Hey, everybody. All right. How are y'all? Look at you guys sitting outside. I don't blame you. How about this weather this week? I wish I was sitting outside. Oh, good. Well, did y'all have a good weekend? Decent? Y'all excited spring break is next week? Can you believe it? It's nuts. Good. I'm excited too. Well, I have been grading exams. I did not get to do a ton of that, or as much as I wanted, I should say, over the weekend. So I would say by the end of the week, so by the end of Friday, everything should be graded. I was just grading 3 minutes ago before I hopped on here. So I'm trying to do it every spare minute I get, just so you know. I know you guys are waiting. But the key is posted, so you can always check that out, look on that. Good. Anything from you guys? No, y'all are good. I will wait just another minute till more people get on, kind of go through some announcements and things like that. And then we are going to jump into chapter 7. So it's going to be good. All right, 10:50. So we'll get started. I'm going to jump over to a slide that I have here on the iPad and share a few things. And before I do that, I really wanted to talk about the exam 2 stuff. I know I sent the email Friday, so hopefully you read all that, and hopefully that's pretty clear. But I did just want to address it in person. So in case you didn't read your email, there was kind of a thing that happened with exam 2, pretty widespread, pretty common. Almost every other exam. I don't know. I'm not gonna give it a percentage, but it seems like at least every third exam that I grade or so. Some common names were given for some molecules, and I'll show you in just a second on the slide. The hydrazine and the butane thing that I was talking about on the email. So anyway, I've had some students reach out after that email and tell me, hey, I sincerely did know the names of these, and here's why. I had one student send me a picture of some notes from a high school class they took. So I know some of you, it's not your first chemistry class. Some of you it is. And so I know you've maybe, learned names of molecules before. But the way I taught you guys the name, we've learned names of ionic compounds. We learned names of binary compounds, right? And those include prefixes or Roman numerals or things like that. But yes, I will be honest, there are common names for molecules such as methane, propane, butane, things like that. It's just that I have not taught those. So I wanted you to practice the naming that we had talked about in class. So when I saw words like hydrazine and butane pop up, it definitely caused me to turn my head as to why you would put those names on. And I will say, what's more alarming to the reason why it really caused me to turn my head was because, again, and there's no judgment. I know people are going to make mistakes on exams, but for me, when I see common mistakes such as you're drawing a Lewis structure and your carbon doesn't have 4 bonds, it only has 3 or 2. Or you're drawing a Lewis structure and you put lone pairs on a carbon.
I'm on the Zoom.
And make sure you're muted, please. And so when there's other common mistakes, but then you have this kind of more advanced naming on this question, it definitely indicates the use of the internet. Let's just be straightforward, okay? So that's why it raised an alarm for me. If you have any questions about this, I'm approachable. You can talk to me about it. It's frustrating from my end, but I put this in the email, and I want to make it clear. If you put that naming on there, you got a 0 on the question, so it's worth 6 points. So it's not going to destroy you, but if a situation does happen like this again, next time, it is going to be a 0 on the exam, because I don't want you guys to use the internet, and I want you to answer the exam from what you have in your knowledge base. I want you to walk away from this course with something to show for it. I want you to walk away from college with a degree with something to show for it. So that's my reasoning behind it. But again, if there's any questions on this, or you want to talk to me about it, I'm approachable. I've had great emails from students and great conversations about it already. But that's how that's going to be handled. And just wanted you guys to hear that from me. So, alrighty, I'm going to jump over to this just so that you can see. Take a screenshot if you want. Just several announcements. One, the key was posted. We already talked about the naming question. Your chapter 7 homework, that's kind of the next announcement. That is up on Mastering Chemistry now. And that is going to be due the Monday after spring break. So I believe that is March 29th. So here's what I'll tell you. A lot of you are probably going to wait till the weekend after spring break to look at this or get into it. And please don't do that. That's going to just create a stressful situation from you and a bunch of emails the weekend after spring break for me. And I want to be able to answer your emails timely. And I probably will check my email like Sunday, the very last day of spring break before we begin the next week after spring break. But I'm not going to be checking it all through spring break. I want you guys to take a break too. Okay. That's what spring break's for. So I would say go ahead and start looking at that homework this week while we're talking about the material. One, so it's fresh on your mind. And then two, you don't have to do it all over spring break. There's that. And then lab grades. I wanted to talk about this for a second because I had a student reach out to me and say, hey, I noticed that I was missing a few points on my lab, but I seemed to put all my answers in the same way my classmates did on, or my lab partners did on from the Zoom meeting. So I was wondering why I got counted off. And I've had a few of these emails. I think we can all agree that Blackboard and having to type your answers in the way we do is all like the most frustrating part of this whole course. It is that way for me too. And I know it's that way for you guys. So I try to set it up to where it'll accept a range of answers so that, for example, if the correct answer is 91.07 grams and you put in 91.06 grams, I want that to be counted correct. Okay, I don't want it to be counted wrong. And I had a situation, I went back in and looked at one student's lab answers, and there were some things that were close like this that Blackboard had counted incorrect. And when I try to set it up, I try to not let it be that way. But maybe I need to do a little more research or stuff on Blackboard. So anyways, I'm just asking you, always go look at your lab grades. And if you notice something that's like, okay, that's off by like 0.01, or it's a really close answer, or if you just have questions about it, please email me. And I want to look into those for you and correct those and give you points for that kind of stuff. Okay. Now, if it's missing units or has wrong units, or it's like, half the answer it should be, you're probably not going to get points for that. But if it's close, or if you just have a question about it, please draw that to my attention. There's 140 or so of y'all. And so it's just kind of impossible for me to go double check back through everyone's grade every single time and make sure of that. So please help me with that. And hey, on the chat, can you make sure it is very specific if it wants scientific notation or just the normal number? Yes, I tried to tell you if it needs to be put in scientific notation, it will say, write your answer in scientific notation. So if it does not say, write your answer in scientific notation, you're just supposed to put the normal number. Does that make sense? I think I got hit on that last time for putting scientific notation. Okay, Haley, why don't you email me and I'm happy to go look at that. And if you put it in scientific notation, but it didn't want that and it counted you wrong, I will give you points for that. Okay. But do make sure that you try to put it in the best way the instructions indicate. So I know sometimes it's confusing, which is why I think it's all the more important that you show up in person to lab. We've had several students, usually lab participations, maybe about 70%. So if you're doing the labs on your own and I'm not there to help answer questions in person, the way people who I can help for people to show up to the Zoom breakout rooms for lab, that's a little more difficult. Okay, so that's another benefit of showing up and having me there to help answer those questions in the moment. So anyways, I'm gonna kind of switch over. I'm kind of done talking about all this. I don't think I have any, so we are doing the enthalpy lab this week, by the way. And Thursday, Friday, that's the one we do. So make sure you print that out and have that ready to go. Okay, I think I wanna get into this right here. All right, it's gonna be chapter 7. When will the exam grades be on Blackboard? So I'm grading all the time. I get a lot of people have already gotten their exam grades back. If you're the 1050 section, you guys are probably all still waiting. So again, I hope by the end of the week. But I just grade them in the order they returned it. That way, it's fair. And so I hope to get to all of you guys by the end of the week. Or I will get to all of you guys by the end of the week. All right, now we're gonna talk about something fun. You should go hiking because the weather's nice. And this is a picture. Anybody been to the White River? It's pretty good for like trout fishing or I don't know, any kind of fishing. Pretty popular spot in Arkansas. So this is kind of northern Arkansas. And the specific place is called Calico Rock. So it's a fun place. You just drive through it. It's really not that big of a town. But you can drive pretty close to this little rock kind of overhang that is in the picture right here. You can just drive there and walk out on it. It's really fun. Bradley says he hunts about 5 minutes from Calico Rock. Good for you, Bradley. Anybody want to go hunt? I don't hunt. I'm not really into hunting. But hunting and fishing, a lot of people do that in this area. So one thing I'm going to tell you though, so this is not really a hike per se. It's just a really, really beautiful spot. If you want to go for a drive, if anybody likes to go for long drives. And if you go here in the fall, especially, that's when we typically will go. We don't go every year, but we've gone a couple years in the past. If you go in the fall, I promise you will see tarantulas. Okay. So every single time we've gone, we have seen tarantulas. It is tarantula mating. Some of you are not looking right now. I hate spiders. Don't look. If you don't want to see it, just don't look right now. It is tarantula mating season in this area of Arkansas in the fall. Okay. So I'm going to zoom in. Anybody want to see it really up close and personal? I'm the one taking the picture. So I got as far away as possible. I hate tarantulas. But literally, we'll see them on the road. We're driving. It's that big. And my husband will stop the car to my dismay. And we'll usually get out and take a picture. So it's happened. I'm serious. Every time we've gone, we've seen them. So just be aware. All right. If you don't want to see the spider, I've scrolled past it now. Okay. We're going to talk about chapter 7, chemical reactions. So we are going to look. Let's see. Let's kind of. Where have we been? We've been talking about chapters 5 and 6, how to write and balance and classify chemical reactions. Hold on. Brandon said, I saw one the size of a bird this fall. Ew. I don't want to know where you saw it. Please tell me you didn't see that in Conway. I don't want to know. I don't think they exist in Conway. I'm just going to tell myself that. But North Little Rock. Oh my gosh. Ugh. Okay. Camp Robinson. Well, I'm not going there anymore. All right, chemical reactions. So we've been talking about how to write them, balance them, classify them. And now we're going to understand the fact that energy, every chemical reaction that happens has an associated energy to it and with it. And that actually determines if it will happen or not. Okay. And then we're also going to look at the rates of chemical reactions. And then this word called equilibrium will be towards the end. But to prove the point that chemical reactions have energy associated, I have the aftermath or examples of 2 chemical reactions here via these pictures and the results of chemical reactions. So in this first picture, anybody recognize what this is? Actually kind of a famous picture. Might not be that famous, I guess, but.
Is it Chernobyl?
Mm-hmm. Very good. This is the aftermath of a nuclear explosion in Chernobyl, Russia. So a whole core of a reactor exploded and released a ton of radiation in the air, and everybody had to evacuate the whole city. Terrible situation. But obviously, chemical reactions, this is a huge amount of energy associated with like nuclear reactors and the chemical reactions that take place there, which is why they're used to fuel energy for like cities and stuff. But there's a lot of fear from the public and just globally with nuclear reactors kind of back in the mid-90s. Because of explosions like this. So anyways, that's just one example. The other example, obviously you can see a lot of heat is associated with the chemical reaction happening here at this race car, and just the friction from the tires and things like that. And so it's giving off a lot of heat. So some chemical reactions give off different kinds of energy, be it in the form of heat or radiation or other things, but just proves the point that energy, every chemical reaction has an energy associated with it. So when we consider the human body, I just want to hear from you guys. What are some main forms of energy that you can think of? We probably won't list everything, but let's start listing some of these pictures. Maybe give you an idea of types of energies that we can think of. I want to hear from y'all. What kind of energy can you think of? Solar, Bianca's, okay, we got kinetic. Yeah, Kendall, we're going to come back to kinetic. That's kind of like an umbrella form of all the different kinds of it. So thermal is definitely one. Okay, so that's like heat, energy. Solar, Bianca, solar. You could also write electromagnetic, okay, like energy from the sun. ATP, Allie, that's an interesting one. What kind of energy, though? ATP is a molecule, so it's not necessarily a kind of energy, but it does contain a kind of energy that I'm looking for. And then Nija, I'm going to come back to potential as well. Autumn says mechanical is good. Static energy, I think you kind of mean like potential energy there. So we're going to come back to kinetic and potential in a minute. But okay, Keegan said it, chemical. So all compounds. Somebody's phone's ringing. Make sure you're on mute. Okay, we got electrical. Thank you, Mackenzie. Electrical energy. There you go. In the picture, this is nuclear energy. That's pretty good. So it's not an all-encompassing list, but this is several different kinds. So energy can have a lot of different forms. And what we learn about energy is that we're never creating or destroying energy. We're going to have a law. We're going to talk about that in a little bit. But energy is just going to be transferred between these different forms. Okay. So trying to think if there's any other I want to write down. I think that's pretty good, at least to illustrate the point. So when we think about the human body a little bit more, what kind of energy does our body run on? You can look from this list. It's one of these. There we go, Bianca. Thank you. It runs on chemical energy. And we're talking about how we, well, actually, I want to go to question 2. How does our body take the fuel we feed it and generate energy? So first off, what kind of fuel? I put this picture of this magazine, this Endurance Sports Nutrition magazine on here because it says fuel your body for optimal performance. This is not a relative of mine, but apparently someone does do like dietetics stuff. What kind of fuel do we feed our body that contains the chemical energy that we need? So how do we acquire the chemical energy that we need? By doing what? By food. Thank you, Bailey. Okay, food and water, and then oxygen. That's the other thing I want to talk about. So we give our body food, and we give our body oxygen, and our body takes these things and it extracts the energy from the food we eat. All food is chemicals, right? And so those chemicals contain energy in the bonds, in the chemical bonds, and then oxygen, which also has bonds. But the sum total, how does our body exactly? Obviously ATP. You guys have probably heard of ATP. That's the molecule for energy for our body. So what is the sum total? How does our body make ATP? I'd like to get a little specific here. Anybody know any of the biochemistry words? How our body makes ATP? Some of the processes that happen for us to make that molecule so that we can then do work. That molecule can provide energy in our body. Protein synthesis, that's an important part of it. Isn't it made from protein? So there's several different things that go on. The sum total, there we go. Mackenzie said a glycolysis is one part. Krebs cycle, now we're getting there. Okay, and then the very last part of this is actually really specific, and I wouldn't expect anybody to know this until you take maybe a more upper level chemistry class. The last part is called oxidative. I'm going to abbreviate phosphorylation. And this is actually the part where ATP is made. Okay, now the sum total of this, all of this is our metabolism. Okay, and there's lots and lots and lots of different things that affect our metabolism. Genetics, our external temperatures, the environments we live in, obviously our diets, the amount of physical exercise that you get every day. Some people you'll hear say, I just have a really slow metabolism. And you may hear other people say, I have a really fast metabolism. And you know what? They very well might. And as we get older, our age tends to affect our metabolism. But all of this works together to create, so we extract energy from the food we eat, and then we create ATP. 36 ATP total, that's right. That's the number. So this is very important when it comes to chemical energy in our body. So I'm really not going to focus on ATP today. We're not going to get into that. That would be more of an upper level class, but we are going to talk about how we're going to go back to this idea that chemical reactions are associated with different kinds of energy. So I have some people typed this in the chat earlier, kinetic and potential. We're just going to define these real quick and move on because we're going to focus on this one today. But kinetic is what kind of energy? The energy of what? Thank you, Kendall. Movement. Okay, or motion. And so like water falling down a waterfall has kinetic energy. Things in motion obviously have kinetic energy. Potential energy is therefore the opposite of that. It's the energy of it's stored energy. All right, like if you think about a hydroelectric dam, you've probably seen some of those. The water is stored behind it, and then as it moves through the dam, it gets kinetic energy, and then it runs the dam. We get electrical energy from that. So that's stored energy and the energy of movement. So we're going to focus on potential energy because it's the chemical bonds in molecules that have potential energy. Okay. So that all brings us to this question. How do we know if a reaction is going to occur? Our body is constantly performing reactions that are favorable to it, and it doesn't want to do reactions that are unfavorable, but there are some reactions, example, the formation of ATP. Oh, Lord, that's no good. Plug my Apple Pencil in while I talk. Formation of ATP is one example of a reaction that is not actually favorable to our bodies. So it has to come up with some mechanisms and some schemes to even perform reactions that don't seem favorable. So how do we know if a reaction is going to occur? How do we know if it's favorable from an energy standpoint? Look at this reaction we have here on the slide. So we have AU and H2O. What is AU? Anybody know? It's gold. So it is gold, yeah. So we got gold and water. So let's say I had a gold ring or a gold necklace or I don't know, a piece of jewelry, and I drop it in a glass of water, okay? That's mixing gold and water together. Am I gonna get a chemical reaction, you think? Clearly we can write products for this, but would we get an immediate chemical reaction? Probably not, right? Now, maybe that reaction would happen over a long period of time, like years and years and years and years, but probably not immediately. So how do we know if we're going to get a reaction? Well, energy determines if a reaction will occur. And I'm going to use this word spontaneously. All right, spontaneously. So what does that mean? Well, to you, something spontaneous might be deciding to do something on a whim. But in the context of this course, a spontaneous reaction is one that will just go on its own. It'll go to completion. You don't have to heat it up. You don't have to cool it down. It'll just run once it gets started. Okay, that's the way we're going to view this word spontaneous. Okay, now this next statement is also pretty key. If the products have less potential energy, there's our word potential, than the reactants, the reaction will occur spontaneously. Okay, so I want to draw an energy diagram to maybe give you a visual to help you understand this. So I'm going to zoom in on the corner, but I'll zoom back out in a minute. So we have some sort of energy diagram, and potential energy is our y-axis. Let's say we have a reaction, and our reactants have this level of energy, this amount of energy. And our products have this amount of energy. So I'm going to put P for products. So clearly you can see the energy level of the products is lower, less. Why is this favorable? Well, as this reaction goes, so as the reaction progresses from reactants to products, we are giving off energy. And what this means is that the products are more, I'm actually going to do this in a different color because it's important. They are more stable. Okay, so our body, these reactions are favorable or spontaneous to our body because when we do reactions that give off energy, our body can harness that energy to then go do other reactions. Our body's constantly doing, I mean, how many reactions a day do you think? You know, billions, trillions to maintain homeostasis and things like that to run our metabolism. So to create, to do these kinds of reactions, that's favorable, and to create products that are more stable. Okay, those are spontaneous. Now, what we're going to talk about today is kind of a big picture. There's different layers and there's different parts to it. So that's why this next thing that I'm about to fill in says 3 factors that determine the energy of reactions. So just remember, this is kind of big picture. There's 3 different puzzle pieces, and we're really going to talk about puzzle piece 1, and we're going to maybe get into puzzle piece 2 today. But the first one is enthalpy. Second one is called entropy. And the last one is called Gibbs free energy. All right. How many of you have heard these words before? You can kind of give me a thumbs up or a thumbs down. Thumbs down if it's brand new to you. Okay. We got a mixture. Some people have, some people haven't. That's what I expected. So we're going to talk about enthalpy first, and then we'll get a little bit into entropy, and we'll save Gibbs free energy for Thursday. Because of the snow day, usually I allot 3 lecture days for chapter 7. And because of the snow day, I had to drop something somewhere. So I had to cut a lecture day for chapter 7. So we're probably going to trim down some of the material, but I'm also giving you a heads up. There may be like 2 10 to 12 minute videos that I post towards the end of this week to finish some of the material that we have to get to set us up for chapters 8 and 9. All right, enthalpy. So
I have a question.
Oh, yes. What's your question?
What was the R in that graph again?
Reactants, Bailey.
Reactants. Okay.
The energy level of your reactants and the energy level of your products. Yeah, great question.
Thank you.
Okay, so before I define enthalpy, I'm just going to talk about kind of the basis of this idea of enthalpy, and then we'll define it in a minute. So I want to read these statements. Reactions occur via the rearranging of bonds. Okay, so we have to break bonds on the reactant side, and then we rearrange the atoms and we form new bonds on the product side. So you need to know that breaking bonds requires an investment of energy. And this is what we do on the reactant side. Okay, we're breaking the bonds of our reactants. The atoms rearrange. We form new molecules, new bonds on the product side. And then on the opposite, from the opposite direction here, forming or making bonds releases energy. And this is always corresponding to the product side, because this is where we form bonds. Okay, breaking bonds requires an investment of energy. Forming bonds releases energy. Now, then that begs the question, so how much energy do I need to break a bond? How much energy are we talking? Well, that's kind of nuanced too, because there's no one straightforward answer. Every bond is different. Every bond includes different atoms. Okay, maybe it's 2 hydrogen atoms, maybe it's 2 fluorine atoms, maybe it's a hydrogen and a carbon atom. So it depends on what atoms are involved. And it depends on the number of bonds. If we're talking like how many bonds are holding those atoms together, 1, 2, 3, whether it's a single, double, or a triple bond, it's going to require different amounts of energy. And to kind of prove that point right here, I've got 2 molecules. I'm going to zoom in, nitrogen and chlorine. So 2 atoms of nitrogen are held together with a triple bond. 2 atoms of chlorine are held together with a single bond. And you can see these numbers associated, the 226 kcal or the 58, they're different based on the atoms and based on whether it's a single or triple bond. So a triple bond requires more energy, 226 kcal. A single bond requires like 1/5 of the amount of energy because there's only 1 bond to break. So that makes sense. By the way, we call these numbers, the 226 kcal and the 58, we call these bond dissociation energies. Okay, you might see it abbreviated as BDE. Okay, a BDE is a bond dissociation energy. All right. So let me zoom out. There it goes. All right. So that's the blanks down here. Bond. That's the amount of energy necessary to break a bond. Now, scientists have done a lot of work and they've looked at several different bonds and they've come up with a whole table of numbers. So the table I'm going to show you next, it's not all inclusive, but it does include several different kinds of bonds. If anybody needs me to scroll up or go back, just let me know. So we're going to be using this table a lot. You'll have this on your resources page for exam 3. I knew it. Can you go back? Yes, I can. Okay. You're going to have this on your resources page for exam 3. So this just shows a bunch of different kinds of bonds. And I want to highlight a few things because I had a question on how to read this. So all of these bonds right here correspond to these bond dissociation energies, these numbers. That's how much energy it takes to break or how much energy is released when any of these bonds are formed. Okay. So you're given 2 different values. You're given the value in kcals. Remember, calories and joules are units of energy. So kilocalories per mole or kilojoules per mole, which is the second number. The next column, all of these bonds correspond to these numbers. Okay. And all these bonds correspond to these numbers. Now, I want to focus on one thing real quick because, look, right here. What's so special? Why is there an asterisk by this CO double bond? Okay. There's an asterisk there, which corresponds to this down here. It says the CO bond dissociation energy in CO2, a molecule of CO2. They're different numbers. Okay. That's kind of frustrating, I know, because it's there will be times you deal with a CO2 molecule. You got to remember to look at the numbers below the table, not in the table. So for any molecule, if you have a CO bond, a CO double bond, so for example, if I had a molecule like this, oops, carbon with hydrogens, and then I had another carbon here and it's double bonded to oxygen like this. This particular CO bond, because it's not a molecule of carbon dioxide, you would just use the 178 or the 745. If I was asking for kcals, you would use 178. If I was asking for kilojoules, you'd use 745. But if it's a molecule of CO2, okay, which looks like this, these carbon-oxygen double bonds, you use the 191 or the 799, okay? I don't know why they're different. They just are based on data that they've collected, okay? All right, so that's the table. We're going to come back to this table a lot. When you do the lab, by the way, Thursday, Friday, we're going to be using this table. So this is actually printed on the first page of your lab. Okay. This picture is just kind of a repeat from the slides above, but I just wanted to point out whether you're forming bonds or making bonds, the numbers are the same. Okay, so it requires an investment of energy to break these bonds, but then these figures right below is the process in reverse. We're taking 2 nitrogen atoms and putting them together to form the bond. And that same amount of energy is released or given off when you form the bond as the same amount of energy needed to break the bond. Okay, does that make sense? And that's what it says right down here. The energy required to break a bond is the same as the energy released when you make that bond. And this is kind of summed up in a law. It's the law of conservation of energy. Our labs in this week in person. Yeah, we are meeting on Zoom still. We are meeting. I know you Friday people are going to want to start your spring break early, but I promise to be worth it if you'll get on and we'll knock the lab out. So we are meeting. Wait. In person. I misread that. We're meeting on Zoom. Yeah, we're not meeting in person. We are meeting. I read that as, are we meeting or not? We are meeting, but we're meeting on Zoom. Okay. We're not meeting in person. I think the week after spring break, we meet in person for Le Chatelet's principle, but not this week. We're just on the Zoom breakouts. My apologies. All right, anyways, law of conservation of energy. Energy is neither created nor destroyed in chemical reactions. It's just transferred, okay, between bonds or released as heat, things like that. Okay, questions so far. We're going to do some practice problems now, so grab a calculator, grab a sheet of paper. We're going to do some poll questions after that. All right, so I'm going to define enthalpy now that we've talked all about it. Enthalpy, we abbreviate enthalpy with an H. Enthalpy with an H. This is the measure of the energy stored in the reactants and the products, okay? It's essentially the sum of the bond dissociation energies for any molecule. The sum of the bond dissociation energies for any molecule, okay? And if you have a whole chemical reaction and not just a single molecule, you can actually measure what we call the change in enthalpy. And we abbreviate this as delta H. So it's the Greek symbol delta H. That is change in enthalpy. And this is for an entire chemical reaction. You can measure the enthalpy just for any molecule or any bond, but change in enthalpy is for a whole chemical reaction where you have reactants and products. That's the difference between the energy needed for breaking all the bonds on the reactant side. Remember, this is for your reactants. And bond formation. This is when you make your products. Okay. First practice problem. We have this reaction. We're going to make ammonia, NH3. So to make ammonia, you take nitrogen gas, you take hydrogen gas, and you mix them together. And this is already balanced for us. So we got coefficient of 1 for nitrogen, 3 for hydrogen, 2 for ammonia. And I actually have the bond dissociation energies listed right down here in the corner. So what we want to do is I want you to add up how much energy total is it going to take to break all the bonds on the reactant side. Here's what I mean. Let's do this together. You got a molecule. First, you need to see what kind of bonds you have. Okay, so the first thing, I'm going to make a little to-do list. When you're doing these kinds of problems, one, you need to have a balanced reaction. Okay, this was already given to you, but if you don't have that starting out, you need to write one. And then two, you need to get Lewis structures. These are going to help you see what kinds of bonds you have in your molecule. You got to count them up. Okay, sometimes there may be more than one kind of bond, or sometimes there may be 3 or 4 of the same kind of bond in the molecule. Got lone pairs there. Okay, so we have one triple bond, and we see that the bond dissociation energy for breaking, if we're going to break this triple bond, it's going to cost us 226 kcal per mole. We also have to break the hydrogens. A hydrogen molecule looks like this, one single bond. But guess what? According to our balanced reaction, we got 3 of them. I didn't draw out more than one nitrogen molecule because my coefficient for nitrogen is just 1. But here I've got actually, you could draw them all out. You don't have to draw them all out if you want to, if it makes sense to you to multiply by 3. But we've got to break every single one of these hydrogen bonds. To do that, each one is going to cost us 104 kcal per mole. So we need to multiply this number times 3 to account for each of those bonds. So total, I'm going to call this, the sum total is the enthalpy of the reactants. What does that equal? It's going to be this number plus that. Haley said she got 538 kcal per mole. Okay. Then on the product side, so everybody good with what we just did on the reactant side? Give me a thumbs down if you're not. Thumbs down? Okay, I'm seeing one. So let's go back. First one, make sure you got a balanced reaction. Step 2, I drew out Lewis structures. This is telling me what kind of bonds I have. I got a nitrogen triple bond and I've got 3 hydrogen single bonds. So I drew out 1, 2, there's all 3 hydrogen molecules. Why did I draw 3? Because from the balanced reaction, I have a coefficient of 3. So I had all these bonds listed here, the dissociation energies, that's where I got 104 from. Or you could go look at the table. I just got these numbers off the table. I just didn't want to scroll up, okay? So I'm just writing these numbers in, and I did 104 times 3 over here because we have to break all these bonds so that the nitrogen and the hydrogen atoms can rearrange so that we can make our molecules of ammonia over here, and we're about to draw those out. Why did you write H reactants in the chat? Okay, remember we abbreviate enthalpy with an H. This is our enthalpy. I am adding up all the enthalpy of the reactants, okay? how much energy it's going to cost us to break all the bonds on the reactant side. All right, so that's why I wrote H reactants. H is just the enthalpy of all your reactants. Other question in the chat, what does the bonds have to do with the problem? Like the number of bonds? Bradley, do you mean, when you say number of bonds, do you mean whether you're talking about a triple bond or a single bond? Or do you mean like writing out from your coefficient how many of those bonds, like double or triple? Yeah. Well, the reason you have to account for whether you have a double or triple bond is because your bond dissociation energies will be different. Like we could go look at this table up here. A nitrogen, oh, let's see. I think I'm pretty sure. Yeah, like a carbon-carbon single bond only costs you 83 kcals to break it, but a carbon-carbon double bond is going to cost you 147. A carbon-carbon triple bond, 201. So you have to take into account what kind of bonds you have because your numbers are going to be different based on what kind of bond you have. Is that okay? Another question in the chat. On the table for nitrogen triple bond, it is 226 and 960. Yeah, so these are two different numbers. So I didn't clarify. We're doing this in kcals. That's why our units are kcal. So I'm using the number for this right here for the kcal. This right here, if I wanted to calculate it in kilojoules, I would just use the other number. Yeah, all great questions. All right, so this is enthalpy of the reactants. Now let's add up the enthalpy of the products. And I promise I'm going somewhere with this, so hang in there. We got nitrogen. This is what a molecule of ammonia looks like. Just like that. So in one single molecule, how many nitrogen, hydrogen single bonds do I have? Three. Thank you, Kendall. I'm going to highlight them. 1, 2, 3. So I've got to break, or I'm not breaking on this side. I've got to form all three of these bonds. And when I form each one of those, each one is going to release 93 kcal per mole, okay? But my coefficient says I have 2 of these molecules. So I could actually, again, you don't have to draw them all out. I like to do this initially just to show everybody how many bonds you're actually forming. We got 3 more in this molecule too. So we got 6 total that we're forming. Each one is going to release 93 kcal. So total, how much energy are we going to release? What you need to do is 93 kcal per mole times 6. If anybody's confused on how I got the 6, please let me know. All right, I'm seeing in the chat, everybody is saying, we're going to call this the enthalpy of the products, H products. That equals 558 kcal per mole. Okay. So we just did a lot of work here. What is all this for? I'm going to scroll down to the next slide. I'm going to wait. I bet somebody's still writing. Okay, so we got the enthalpy of the reactants, enthalpy of the products. So I'm going to scroll. If you need me to go back, let me know. So now, ultimately, what we're trying to do is we are trying to solve for a delta H. We just calculated kind of the static enthalpies of the reactant side, the product side. Now we're going to put them together and get the total change as this reaction happens. How is the energy changing? That's kind of what we're getting at. So delta H is this. It's an equation. It's the enthalpy of the reactants minus, it's a huge minus sign, minus enthalpy of the products. So we're just going to subtract those numbers. In your textbook, you'll probably see them put this little Greek symbol for sigma. This just means the sum total of that side minus the sum total of this side. But we already did that, okay? That's what we do when we add everything up. And when you add everything up to get it correct, you've got to account for the number and the kind of bonds in your molecule and the coefficient for each molecule, okay? To get the total number of each kind of bond, all right? Okay, so you see these numbers summarized right here. So if we want the delta H, we're going to do 538 minus 558. So our delta H is going to be what? Negative 20 kcal per mole. Okay, great. What does this mean? What is our body see. What does this mean from the standpoint of things like our bodies and our health? When we are running chemical reactions, that something has a negative delta H or a positive delta H. Well, what it means is that overall heat is released. When that happens, your delta H is negative. Okay, that's what we have in this scenario with this reaction. For our bodies, this is favorable. You guys remember the energy diagram I drew? When we have reactions, like when you hydrolyze, when you make a molecule of ATP, and then ATP travels around to your body, and ATP is hydrolyzed, meaning it breaks apart. That reaction gives off a lot of energy, okay? That is a negative delta H reaction. And then that energy is used to power other chemical reactions. Say your cell needs to repair its membrane, or say your cell needs to make a protein, whatever your cell needs to do, if it needs to replicate your DNA. We have to have reactions that give off energy to power other things in our body, okay? So this is favorable to our bodies. A negative delta H is a reaction that's giving off energy, okay? Overall, if heat is absorbed in the reaction, the delta H is positive. Okay, is this making sense? Is this clicking a little bit? Okay. So we're gonna look at one more example. Keegan says, you'll get there. And then I promise the lab, you'll really get there because we're gonna be practicing this stuff right here. We're gonna look at one more example of a reaction, and we're gonna do a few poll questions. So another example is we've got nitrogen and oxygen, N2 and O2, coming together to make a molecule of nitrogen monoxide, actually 2 molecules of nitrogen monoxide. And it's balanced for us. We got coefficients of 1 on the reactant side, a coefficient of 2 on the product side. And then listed just below, we have the bond dissociation energies. Remember, this is B, D, E, for each of these bonds. The nitrogen triple bond, if you draw out a molecule of oxygen, it's an oxygen-oxygen double bond. That costs 119 kcal of energy to break apart so that these nitrogen and oxygens can rearrange and give you your product molecule. And when you form the bond between nitrogen and oxygen, you give off 151 kcal per mole of energy, okay? Now, these numbers we don't have to multiply by anything because the coefficient is 1. But this number over here, we have to multiply by 2 because we're making 2 of those. So we're forming 2 of those bonds, 2 of that kind of bond. So that's a terrible 2. All right, so total, we should have 302 kcal per mole. All right, and then what's the sum total? What is our enthalpy of reactants here? I guess I have a space for that just below. Heat input is the total, sum total of this. This is our H reactants. That is 345, so we just added these together. And then our heat output was 302 kcal per mole. And so what is our delta H gonna be? If we subtract these, 345 minus 302. It's a positive 43. All right. So this is different than the previous reaction because this is a positive delta H. So what this means is we had to invest more energy on the reactant side to break apart all of our bonds. So overall, from the viewpoint of the chemical reaction, we are absorbing more energy. We take energy in to break bonds, and we give energy off when we form bonds. So if we're the chemical reaction, we're absorbing this much energy and we're giving off this much energy. We absorbed more than we gave off. So overall, 43 kcal per mole more energy for bond breaking is needed than what is released in bond formation. So overall, heat input, okay, heat is another word for energy, right? So you might hear me use those words interchangeably. So we're adding heat to this reaction or we're absorbing energy. Same thing there for this reaction. So this again is kind of a summary of what we've learned so far. When heat is released, overall your delta H is negative. And then what we saw on this slide right here is that if heat is absorbed, when you do the subtraction between the enthalpy of the reactants and the products, your delta H is positive. Okay, Alexa says, can you slow down just a little bit? I can. Do you want me to repeat anything? Janaea says, I'm confused on the first example. Why didn't we multiply the 3 and the 2 on H2 like we did for 2NH3? Okay, let me scroll up to answer Janaea's question. One more slide. I'm going to erase a little bit so we can see. And let me erase. Okay, so, okay. This 2 right here does not tell you the number of bonds in the molecule. It tells you the number of atoms. There's 2 hydrogen atoms in the molecule, right? This 3 tells you that you have 3 hydrogen molecules overall. So when you draw all 3 of these out, you see these little dashes right here that I drew, and then I drew the little squiggle through it, indicating that I'm breaking it. That's the number of bonds we're accounting for. Okay, that's the number of bonds I'm accounting for. Now over here, this 3, again, does not tell us the number of bonds. It just tells us the number of hydrogens attached to that nitrogen. Now, it just so happens to correspond to the fact that there's 3 hydrogen-nitrogen single bonds here. And then we do multiply over that all by 2. But the subscripts don't necessarily tell you the number of bonds. That's why I beg you, please draw the Lewis structures out and then actually count your bonds and then multiply by the coefficient. Does that help, Janaea? Okay. This stuff it's not easy. Is it complicated enough for you yet? Okay. I think I put that table on here again in case we needed it, but I'm gonna scroll past this because I want to get to this slide. Okay. I gotta keep an eye on the time. So let's do a recap. This was the first reaction we did. This was the second reaction. We just did these. We just calculated the delta H for these. And you'll hear me say change in enthalpy or delta H. That's the same thing. Your delta H is your change in enthalpy. So if heat is released and delta H is negative, we have a specific word we use to call reactions like this. We call them exothermic. Okay, thermic is kind of indicating that heat is involved, right? Thermal is a word for heat. Exo means that heat is exiting the reaction. Okay, so to us, we're the surroundings. To us, if we were doing an exothermic in a test tube, do you think we would feel heat or do you think it would feel cold? For an exothermic reaction, if you're doing a test tube, do you think to us, the test tube would feel hot or feel cold? Okay, we're getting different things. Most people are saying heat, yes. If heat is exiting the reaction, we, the surroundings, are gonna feel the release of that heat. So our test tube would get hot. So exothermic reactions release heat and we feel that. Okay, on the opposite side, if heat is absorbed and delta H is positive, the reaction is endothermic. Endo meaning heat enters into the chemical reaction. It's absorbed overall. So to us, the surroundings, is that test tube, if we're doing an endothermic reaction test tube, is it going to feel hot or feel cold? If it's the opposite process, it should be the opposite, right? So yes, test tube here would get cold. Endothermic reactions absorb heat and we feel the absence then of the heat. Feels cold to us. Okay, so that's a little bit of a review. Remember the words endothermic, exothermic on your lab this week. You're going to be calculating a delta H and then it's going to ask you, is the reaction endothermic or exothermic? Okay, and you can just look at the sign. If it's negative, exo. If it's positive, it's endo. All right, poll question. I want to see how well you've learned what we just talked about. There's 4 questions, so make sure you answer all 4 here. Are these endo or exothermic? So you're looking at if heat is released or if it's absorbed overall, or you're looking at the sign of your delta H. Bradley says, what do you mean by plus heat? So when you see something like this, to you, would you guess in this reaction number 1, is heat being released as a product or is it being absorbed as a reactant? Okay, that's what you need to think about. And then from there, from what we just talked about, does that mean it's exothermic or endothermic? Like, does that mean absorbed? On this side, Bradley, heat this is your product side. So here, heat is a product. In other words, you could say heat's being produced. On this side, heat is on the other side. Heat is on the reactant side. I don't know if I answer your question. I'm trying to indirectly answer it without just saying it. So on the product side, it's being produced. If it's on the reactant side, it's being absorbed. All right, we've gone for almost 2 minutes now. We've got 70%. Go ahead and get your answers in. We're going to go over these. So if you just have to guess for now, that's okay. That won't be okay in 2 weeks. All right, I'm going to end the poll. We're 90% voted. All right, share results. Okay, here's what everybody said. Number 1, everybody said most people said exothermic, 82%, and that's correct. This is exo, okay? So if heat is on the product side, if it's written into your reaction, the word heat or a number like, 23 kcal, if you saw it that way, this way, or this way, that is exothermic. All right, heat's being produced. If it's on the other side, if it's a reactant, overall heat's being absorbed. And if you scroll up, if heat is absorbed, we said that is endothermic. All right, 3 and 4 are actually the opposite of each other, if you notice that. Here you have A plus D makes AD, and your delta H is a negative value. So we said if delta H is negative, that is exothermic. You could write heat in as a product on number 3, just like number 1. Number 4 is the opposite. You got AD breaking down into individual elements, A and D. Here, your delta H is positive, okay? So this is opposite, it's endo. And you could write heat in as a reactant, just like on number 2. Okay. Questions on this? So number 2, most people said endothermic, 3 exothermic. So yeah, most everybody got it. Good. All right, let's keep moving on, unless anybody needs me to go over this again. Okay, we're gonna work this one more problem. And then at the end of this, we got another poll question. Then we're gonna move on to puzzle piece 2. But we really only have, we got about 20 minutes left. Haley in the chat, as a general rule, heat on the product side will always be exo. Yep, as a general rule, that's good. That's correct. Okay, we got another reaction here. This is actually a combustion reaction. I knew you all knew that. I knew you were thinking this is a combustion reaction. And CH4, this does have a common name. Anybody want to tell me the common name of this? Too soon to make jokes about it. Methane, right? This is methane, okay? Delta H is negative 213 kcal per mole. Okay, so this is an exothermic reaction, right? That's the first question. Exothermic because your delta H is negative. All right, how much heat is released? That's the question we're going to answer right here. How much heat is released if scenario A, we do the reaction with 0.3 moles of CH4, methane? Okay, 0.35 moles of CH4. So how do we answer this? We need a conversion factor. We need to convert from moles of CH4 to kcals. And we're going to do that. I'm going to teach you how to look at this reaction and pull out a brand new kind of conversion factor that involves energy. So I see that my coefficient is a 1. For every 1 mole of CH4 molecules, plus the other stuff, plus the oxygen, I'm going to produce 213 kcal. When I say produce, that takes care of the negative part. Okay, if we're producing heat, that's viewed negatively by the reaction. We're losing heat. So I'm going to write a conversion factor from that. For every 1 mole of CH4, I'm not going to include the negative here because I'm just looking for the absolute value of the energy. We get 213 kcal of energy is associated with that. Okay, so do you see, I just looked at the coefficient and then I just wrote that related to the number. So now using this conversion factor, I'm going to start with the 0.35 moles of CH4. And I'm going to convert. I'm just going to cancel moles of CH4 and convert to units of kcal because that's energy. When it says how much heat, another word for heat is energy. We know units of heat or energy is kcal. So that's how I knew I needed to convert to kcal. All right, so I'm going to cancel for every 1 mole. It's 200 CH4, 213 kcal. So this is just a one-step conversion problem, but this is kind of new because we've never done one with moles and kcals before. Then we just cancel that and we do 0.35 times 213. Okay, so Haley says she got 74.55 kcal. Is that what y'all got? Anybody get something different? Okay, same question for scenario B. How much heat or energy is released? So again, we're looking for units of kcal here. But this time we're just given 7.5 grams of CH4. So I bet somebody knows what to do. What should I do to answer this one? This one's going to be the same as part A. There's just going to be an additional step on the front end. So we're going to use this again. I'm going to bring it down here. Grams to moles, then moles to kcal. That's what Kendall says. I agree. So we're going to first do grams to moles. How many grams of CH4 is in 1 mole of CH4? So guess what? We need a molar mass. So I'm not going to take a ton of time to calculate that. Carbon is 12. Hydrogens are 1, right? So you got 4 hydrogens. So 4 and 12, that should be like 16.05, somewhere around in there. So now I have moles of CH4. Now I'm basically looking a whole lot like I did in part A. I just have, if I calculated this, I would have a certain number of moles of CH4. And what we did last time was we just canceled moles of CH4, plugging in that conversion factor for every 1 mole. It's 213 kcal. Okay, so first we canceled grams, then we canceled moles. Okay, so 7.5 times 1 divided by 16.05, or you could just do 7.5 divided by 16.05, and then you're gonna do times 213. What do y'all get? 99.57 kcal. Okay. So once you calculated delta H, now you can do conversion problems with units of energy. I know you are all excited about that. All right, I got another poll question. And based on kind of what we talked about earlier and this statement just below, launch the poll. In an exothermic reaction, products, are they more or less stable? The word here is stable. I'm not asking do they have more or less energy. I'm asking are the products more stable or less stable? We talked about that. We wrote that in on our energy diagram. This makes the reaction, does it make it favorable or unfavorable? Don't read. I realized the answer was on the slide. Okay, we're 67%. Go ahead and get your vote in. Wait just another second. Okay, I'm about to turn it off. All right, in the poll. Share results. So most people said in an exothermic reaction, remember you're giving off energy. You guys remember the diagram we drew? It looked like this. We said if you got potential energy and you've got your reactants up here and your products down here, so R and P, reactants, products. If the products are lower in energy because it's an exothermic reaction, they're more stable. Okay, so the answer here is that they're more stable. Lower in energy, more stable. Higher in energy, less stable. This makes the reaction favorable. Okay, it's favorable to our bodies. Why? When we do reactions in our bodies that release energy, that energy is used to go do work. Okay. All right. So that's puzzle piece one. Remember we said big picture, there's 3 pieces to the puzzle. Enthalpy is not the only factor when determining the spontaneity or the favorability, if something's favorable or unfavorable, of a reaction. So we're going to move on. I do have a couple more problems you could kind of look over and test yourself or practice, but I'm going to do some review before exam 3, and I'll probably come back to these problems, but they're good problems to work if you want to look at them or ask me questions. I'm going to skip over them for now to talk for the last 10 minutes about piece number 2. All right. So I want to ask you this question. Are all, keyword all, exothermic processes, this is a fancy word for reactions, spontaneous? Remember the word spontaneous means favorable. And are all endothermic processes, so exothermic was the negative delta H, we just said is favorable to the body. Endothermic is the positive delta H. Are all of these kinds of reactions non-spontaneous, or in other words, are they unfavorable? Okay, so that's a big question. We're using the word all here. We could say usually, that's what we said up here. In exothermic reactions, the products are more stable and the reactions are more favorable. But can we say always? Well, let's read this statement just below. Consider the statement. If you sit ice on a plate, so you take it out of the freezer, you just put it on a plate, it will absorb heat and melt. So I want to ask you, this process, what we have is we have ice, which is water as a solid, right? This is ice. What's happening? It's becoming H2O liquid. This is the reaction. And this process we call melting, because what's happening, it says it's absorbing heat, so we're adding heat. I mean, we aren't adding it, right? But you did move it to a warmer environment. So is this process, I want to ask you, is this exothermic or endothermic? Okay, I'm seeing both. Seeing both. Okay, so absorbing heat. Remember, absorbing heat. If you're absorbing heat, you're endothermic. If you're releasing heat overall, you're exothermic. Okay, so if you're absorbing heat, this is endo. So we have an endothermic process, and then I want to ask you, is this going to happen spontaneously, or do you have to put that ice in the microwave? Or do you have to put that ice on the stove and turn the burner on? Or is it just going to happen, whether you do anything or not? You did take it out of the freezer, but once you take it out of the freezer, once the process of melting starts, yeah, just going to happen, okay? So this is spontaneous. In other words, this is favorable. So we just answered our question. No. That's an N. No, not all processes that are exothermic are favorable. Some processes that are endothermic happen to be favorable. Ice melting, okay? So what's the big whoop about all this? Why do we care? That just means there's another piece of the puzzle, and that piece is our entropy piece, okay? The reason this whole ice example, it's a silly example, I know, but the reason this happens is not because of enthalpy, it's because of entropy. This is driven by entropy, not enthalpy, okay? So that's why we got to talk about this guy. What is entropy? Entropy, we abbreviate with an S. This is a measure of disorder in a system. Another word for system is our reaction. Okay, you might hear me say system or reaction. That's your chemical reaction. All right, delta S, just like delta H, this is a change in disorder as you go from reactants to products. Okay. So here's our units for delta S. I want to look at these. It's calories per mole Kelvin, right? K, remember what K stands for? This is Kelvin. This is different from delta H. Delta H was just kcal or kilojoules per mole. So there's some differences. I want to look at the differences on these units. Number one, calories, not kcal. So what that means is that changes in entropy tend to be smaller. That does not mean that they're not significant. It's more appropriate to use a smaller unit. Number two, we have units of Kelvin in the denominator. Whoops, I'm not spelling this right. Kelvin. So what that means is that entropy is temperature dependent. Okay, the ice doesn't melt spontaneously until it's in a warmer temperature. Temperature dependent. All right, so this is really important too. Processes for which delta S is positive, meaning disorder increases, okay? Those tend to be favorable. What just happened? I don't know. Favorable or spontaneous. Okay. Okay, this is a lot. We're almost done. 4 minutes left. Hang in there. This is going to be the last slide we talk about right here. Questions so far on anything I just wrote? It's kind of just some preliminary definition stuff. Now we're going to look at a figure that's going to help us assess for any chemical reaction I give you. You should be able to tell me delta S is negative or positive. Okay, so how do we do that? This is kind of some repeat of above. Delta S is the change in entropy. So obviously if delta S is positive, disorder, entropy is increasing. Delta S is negative, entropy decreases, right? I thought you guys maybe just didn't have enough disorder, in your personal lives to handle and to work with. So I wanted to give you some more disorder to manage and to think about. I don't know about you. I can literally vacuum my whole house on like a Friday. And then by Sunday, there's like Cheerios all over the floor and, cheese in the sink somehow, my bathroom sink, and who knows, stuff everywhere. I know nobody else deals with that. It's just me. But disorder is always increasing at my house. Okay, so let's look at this figure. This is straight from your textbook. And I think this figure is key. So how do you read it? I'm actually going to erase that line I just drew because I want this space over here. If you read this figure from left to right, the way you read a sentence in a book, entropy is increasing. So what that means, two things matter when it comes to a measure of disorder. One, the physical state of your reactants in your products, okay? So we're talking solid, liquids, and gases. Gases are the most disordered state. You guys remember when, I'm going to zoom in. When we drew pictures of gases, we drew these molecules really far apart and they're just zooming by one another really fast. Liquids, the molecules are a little closer together and they're fluid, so we drew some arrows. Solids, we said the molecules are really close together. They're very ordered. Gases are disordered a lot. So if you have something like ice melting from solid to liquid, disorder is increasing simply because the physical state of the matter is changing. Or if you have, for example, a synthesis reaction where you have more reactants and they're combining to make one product, that's what you have down here. You have fewer moles. Sorry, I said that backwards because we're talking about entropy increasing right now. If you have a decomposition reaction, okay, where you have one thing breaking down into multiple things. So you're starting with fewer moles on the reactant side, and you're ending up with more items or more moles of items on your product side. Entropy is increasing, disorder is increasing. Two things are more disordered than one. Three things are more disordered than two. Now, if you read this whole figure in the reverse way, like you have a gas that's condensing to a liquid or to a solid, you're becoming more ordered. Or if you have more moles of stuff, and they're combining like a synthesis reaction to give you fewer moles, which is what we have right over here, entropy is decreasing. Okay, so look at this reaction. It's the last thing I'm gonna say, and then we're done because we got 1 minute left. I have one mole of nitrogen gas. I have 3 more moles of hydrogen gas. So total, I have 4 moles of reactants. I'm just going to abbreviate R for reactants. Over here, I have 2 moles of ammonia gas. So I have 2 moles of products. Now, everything's a gas, so we really can't make a judgment call based on the physical state. But I see I have more moles of stuff, and then I'm making fewer moles. So delta S is negative here. You're becoming more ordered. So disorder is decreasing. Okay. All right. Bet your brains are fried enough. That's it for today. We're going to pick up with this slide on Thursday. I'm going to keep the slide up. I still see some people writing. If you have questions, I'll stick around for a few minutes. Take a break, take a breather. You're going to have a quiz Thursday. Chapter 7 homework's up on mastering chemistry. So again, that's not due till after spring break though. Thanks for joining today. I hope you guys have a good day.
When will the lab be due?
The enthalpy,
Yes, ma'am.
that's due Sunday night. So you got to get that done kind of before spring break, which is why just join the labs, the Zoom sessions, and you can knock it out then. You said quiz Thursday? I did. Quiz Thursday. It'll be on this stuff.
Okay, I got a question.
What's up, Kishan?
Okay, back when you were doing the like the N2 plus O2 equals 2NO, where did you get the 226 kcal per mole?
Oh, right here. From the table.
Oh, okay. I don't
Yeah,
know.
anytime you see a number like that, it's going to be off this table.
Okay. Let's see.
It's a lot. We covered a lot today.
Yeah, I think I got it though. Wait, wait.
Good.
Yeah, I think I got it.
Okay.
If I got any questions, I'll just email.
Please do. Would be happy to talk through those things.
All right.
Thanks, Kishan. You have a good one, okay?
All right, you too.